for the introduction, Mark. Thanks for inviting me to speak in the seminar. Thanks for attending. I should say I'm a postdoc at the IAS. As a trade-off for giving this talk, I was not forced to give a postdoc talk, which is why I was not in the series, but I am a postdoctoral. And so this is also, I guess, for this year, a bit of an intro to my research. Okay, let's get started. So the main actors in this talk will be covering spaces. So specifically covers of manifolds. I'll start with the connected orientable manifold. And what I want to sort of study are covering spaces. So what are covering spaces? So a manifold is a covering space if around each point there's a neighborhood such that the pre-image of a neighborhood is the proverbial stack of pancakes, right? Is a disjoint union of copies of that neighborhood. That the number of copies is independent of the neighborhood you choose. And we call that the degree of the map, so sort of the size of the pre-image of a given point. And the third important in the talk will be the fundamental group of X. So the group of based loops under, I've forgotten the word when you do it twice. Composition, yeah, exactly.
I don't consider branch point.
Pardon me?
No branch point.
No branch points, actual covering space. There will be secret branch points, which you will see immediately, but no branch points. Okay, why is the fundamental group important when I study covering spaces? Well, because there's a correspondence between finite degree connected covers of a space X up to isomorphism and finite index subgroups of pi1 of X up to conjugation. And in this talk, I'll make ample use of this. When I want to talk about a cover, sometimes I'll just take the shorthand and talk about the finite index subgroup of the fundamental. So that'll be sort of a language that I shift between during the talk. And the degree, to give you an idea how this correspondence works, sort of the only invariant we've talked about so far, the degree is actually the index of this finite index. So, okay, so here's an example. The circle has fundamental group Z, right? There's only one way to, well, you can go around, the loop just goes around the circle in one of two directions a certain number of times. The finite index subgroups of Z are, here's MZ for M and N. The M has disappeared in this version of the slides. And to that integer N, M corresponds to the cover in which you coil this circle around M times. So if you look here, yes, it is a cover. Around each point on the circle, there's sort of 2 points in the cover of degree 2, 4 points in the cover of degree 4, etc. Right? If you take a tiny neighborhood of a point on the circle, you'll have really 2 little intervals or 4 little intervals. Okay, maybe not in the degree 4 one, but that's due more to my failures as an illustrator than actual covering space theory. Okay, so I'm not just going to study covering spaces. In the title, there's towers of covering spaces. So what's a tower? Well, it's a sequence of covers of a base space X naught, such that each space in the tower are sort of successive covering spaces of one another. And I'll be interested in the degree of these covers, but not in the degree from X2 to X1. I'll always sort of take the degree relative to the base space. So I've sort of written it here. D1 is the degree between X1 and X0. D2 is the degree between X2 and X0, et cetera, et cetera. Okay. As an example, if I want a tower of covers of S1, well, I have to take sequences M1, M2, M3, such that M1 divides M2, M2 divides M3, M3 divides M4, et cetera, et cetera. For example, and this will be a recurring theme in the talk, I could take Mn to be p to the n for some. So you see the bottom of the tower of 2 power towers. And the question I want to answer is the following. So if I have a tower of covering spaces, how complicated do the spaces get? Of course, this is a very vague question, and I'm going to refine it. So what will be our measure of complicated? In this talk, it'll be the first Betti number. So the first Betti number will be sort of our numerical invariant that will measure how complicated a space is. It's the dimension of the first homology with rational coefficients. If you haven't computed the first homology of something in a long time, that's okay. Neither did Betty. So this is an excerpt of, or the relevant excerpt of his text, Sopra I spazi di un numero qualunque di dimensioni, where he begins studying spaces of higher dimensions. I was hoping there would be Italians in the room. I'm not sure there are, but if there are, while they're reading this text, let me tell you a few things about Betty. He was an interesting guy. He was sort of at various times in his life, a soldier, a teacher, a math professor, and a senator in the sort of parliament of the newly formed Italian state. And let me also tell you that I read about him in the recent English translation of Poincaré's works, and the people who wrote the preface to the translations that said that Betty was the only person who had made significant contributions to topology between Euler and Poincaré. So, yeah. Anyways, okay, so what does this mean? This is my translation with some help from Google. So instead, I want to tell you instead of what, if in X, we can imagine a number B1 of closed spaces of dimension 1, so loops, and we cannot realize them as the boundary of a connected part of a two-dimensional space, all contained in X, and such that every other, if I add another one-dimensional space to this set, then actually I can make that into the boundary of a connected dimensional space. We will say that, so he calls it having a connection of the first kind of order B1 plus 1. In short, B1 of X is the maximum number of curves or of loops that you can embed in X, and which you can't realize as the boundary of a surface that's also embedded in X. So the canonical loop that you can realize as the boundary of a surface is the boundary of a disk. If you have a contractible loop, really what it does is it bounds a disk, and since you can contract it, you don't count it in homology. Okay, that's what I'll say about first homology. And so the precise question that I'm going to ask is, if Xn is a tower of covering spaces, how fast does the first Betty number grow as n goes to? Okay, let's go back to our example of the circle. In that case, okay, well, first Betty number of the circle is 1. There's only one loop. Sort of, if you put two loops, they're the boundary of a collapsed annulus in which both sides of the annulus have met. And in this case, well, each finite connected cover of all the covers will be connected. Each finite connected cover of the circle is itself a copy of the circle. And so the first Betty number is 1 all the way up the tower. So nothing. In general, the answer will depend not only on the base space, but on the tower. And so this talk, sort of as the talk progresses, will sort of shift from looking at the space to sort of looking at interesting towers. And in general, what I will compare is the growth of B1 to the degree of Xn to X0. And just to introduce some notation, I'll say that f of n is bounded by g of n if f of n is less than a constant times g of n. And I'll say that f of n grows like g of n if they're both bounded by b. Okay, so I'm repeating the question just so we have the question in mind. With that in mind, this is the outline of the talk. I'll first tell you everything I know about spaces of low dimensions. Then I'll talk about arithmetic manifolds, which provide me with these interesting covers, and about some conjectures that are made that sort of guide the work on arithmetic manifolds. Finally, I'll talk about some results as advertised, which form a topological application of the Langlands program. Okay, so I've told you all I know about the circle. So if we want interesting connected closed manifolds, I'm going to go to surfaces. So here's a reminder. Surfaces XG are classified by their genus, so the number of handles. And okay, so the first Benny number is 2G. I've drawn sort of a proof by picture that the first Benny number of the surface of genus 2 is 4. So I've sort of drawn the 4 loops that are not that don't form the boundary of a surface, but if I added one, I could form the boundary of a surface. And that's the invariant we want to measure, of course. The important thing is it's proportional to the genus. And that second invariant I want to talk about is the Euler characteristic. And so a reminder, the Euler characteristic is the invariant that you get by taking a triangulation of your space and counting the number of faces, which is missing an S, minus the number of edges plus the number of vertices. in any triangulation. So here's the triangulation of the two-sphere. You can count that the Euler characteristic of the two-sphere is equal to 2. I grew up in Montreal, and a great perk of growing up in Montreal is that there's a very nice triangulation of the two-sphere. So this is the biosphere. It was the US Pavilion at the 1967 World Fair, and now it's a science museum, and you can go visit it if you ever go to Montreal. Anyways, if you take this triangulation, which is of course a little bit more complicated, you should also get that the Euler characteristic is 2. By the way, this fact that the Euler characteristic is independent of the choice of triangulation. Triangulation is Euler's contribution to topology from the preface of the translation of Poincaré's work. So you're welcome. Now I've told you all the topology that's worth knowing before the arrival.
There's a boundary on the bottom, right?
Yeah, there is a boundary on the bottom, sadly. It was designed by Buckminster Fuller. Yes, there's sadly a boundary. Okay. Here's another example, is the triangulation of the surface genus 3. So in this case, the Euler characteristic is not. And the useful fact, which a triangulation like this should convince you of, is that if I have a cover, the Euler characteristic of the covering space is the degree times the Euler characteristic of the base space. And you can see this because every little triangle is going to, if I make the triangulation small enough, is going to go to d little triangles in the top. And so this formula faces minus edges plus vertices will multiply. Okay, now that I have told you all this, let me tell you examples where we don't need it. First is genus 0, the two-sphere. It has trivial fundamental groups. And so going with our bijection between finite covers and finite index subgroups, but the two-sphere has no non-trivial covers. On the other hand, the torus has some interesting non-trivial covers. So this is the genus 1 surface. Its fundamental group is z plus z, so finite index subgroups are of the form mz plus nz for pure integers m and n. And that subgroup corresponds to unwrapping the sort of two fundamental loops in the torus, m times and n times. So I've drawn here what I call the 3-1 map, in which the orange loop gets unwrapped 3 times. And so that produces 3 copies of the pink loop. As was the case with the circle, any cover of the torus is a torus. And this is not innocent, it's because the torus is really just a product of S1 cross S1. So any cover of the torus is the torus. So the first Betty number is 2 in any tower, and we're still not in a very interesting situation. Okay. On the other hand, things get funky with surfaces of higher genus. So I'm reminding you up there that the first Betty number is proportional to the genus. So really what we want to know is how fast the genus grows in a tower of surfaces. And so here I've shown a tower whose base is the surface of genus 2. So that, well, you can see where the pink loop and the orange loop goes. You sort of cut along the pink loop and sort of paste 2 copies and glue 2 copies together, and then you do it again. But, okay. So what did I tell you? The Euler characteristic scales with the degree, so that's going to be useful. Since the Euler characteristic is 2 minus 2g, well, we can compute the genus of the nth step in a tower in terms of the degree. So by sort of just simplifying the equation, 2 minus 2gn is equal to dn times 2 minus 2g naught. So get this. And what that tells you is that the genus of the nth cover is the degree times g naught minus 1 plus 1. And so in this case, in any tower of higher genus surfaces, the first Betty number will grow proportionally to the degree. So we're in the first example where it's not just constant, and actually it grows with the degree. Okay. And here we also see sort of the first use of it's not actually equal to the degree. Sort of, there's some error terms that we get rid of. Okay, I've told you all I know about surfaces. Now let me tell you one example about 3 manifolds.
Sorry, before you go on.
Yeah.
What happens for surfaces which are not oriented?
Sorry, what was the question?
What happens for surfaces that are not orientable?
Okay.
Okay, the first answer is I don't know. The second answer is I think this Euler characteristic trick should work. I don't see any reason why not. Okay. So yeah, let me start with, or let me give you an example for three manifolds. So xk will, so k will be a knot, xk will be a knot complement, so it'll be sort of the three sphere minus k, which you can draw as sort of R3 minus a knot, sort of minus a knotted line. So here I've drawn the complement of the trefoil knot. So in this image, sort of the knot is missing. So there's a map. So again, I want to go between subgroups of the fundamental group and finite covers. And the way I'm going to do this is I'm going to consider a specific cover. And so it comes from the fact that there's a map from the fundamental group of the knot complement to Z, sending a loop to the number of times it goes around K. So this is the map from pi1 to its abelianization. Anyone who's thought about it, to H1 really. And Z is nice because, as we know, Z has all of these nice finite index subgroups corresponding to the integers, so we can play this game again. And so the mth cyclic cover will correspond to the kernel of this map to Z and then to Z mod NZ. So we play the game again. So then you repeat, you take a sequence of integers that divide each other, for example, powers of P. And in that case, the theorem of Fox that the first Betty number of xm is periodic in M. And so it won't be necessarily periodic of the tower because we're not going to go 1, 2, 3, 4, 5. We're going to go like 2, 4, 8, whatever. But in any case, since it's periodic in M, it's bounded. At some point, you sort of loop back. And not only that, but Fox tells you explicitly how to compute the first Betty number from the Alexander invariants of the knot K. If you don't know what the Alexander invariants are, that's okay. I'm not really sure I do either. The point is these first Betty numbers are explicitly computable, and the Betty numbers are bounded. Okay, so this was an example of a tower of 3 manifold. Let me recap what I've told you so far. In dimension 1, we have the circle. Any tower has constant first Betty number or proportional to constant. Same for the torus. For higher genus surfaces, it grows like the degree, and for knot complement, well, in the specific case of cyclic covers, the growth rate is constant. Okay, here's a remark. In any tower, the degree is an upper bound. Like you're never going to go faster than the degree. So the question is, how much slower than the degree? You can see this again by the triangulation, because if you've ever computed Betty homology, you can compute it from the triangulation. And the number of cells that you're going to use to compute it is going to be bounded by the degree asymptotically. So the first Betty number is going to be bounded by the degree. And so you could ask, with this great table, is it the case that the only two possible rates of growth are nothing and proportional to the degree? And if this was the case, we wouldn't be here. And so for the rest of the talk, I'm going to talk about some more interesting examples in higher dimensions. Before I do that, let me go back to surfaces for a second. So here's a general recipe to make towers. Or right now, a recipe to sort of make manifolds that have a desired fundamental group. Gamma is a discrete group. To make a space whose fundamental group is gamma, what you need to do is find a nice contractible space for gamma to act on. And then, so with a suitable action, so discretely without sticks points. And in that case, you can take the quotient by that action, and the quotient will have fundamental group. So going back again to our favorite example, if I want to produce the circle, I can take the real line and just have Z act by translations. And when I take the quotient, meaning I identify things that are one integer apart, I get the circle that has fundamental groups. It's another example. So SL2Z acts on hyperbolic space, and the quotient here is a surface with punctures called the modular curve. Here, kind of requisite warning. It's not actually a manifold, and its fundamental group. It's actually an orbifold, but it doesn't hurt for the purpose of this talk to imagine that it's a manifold. So this is going to be sort of, it's a famous group action, I guess, and I'm going to talk about generalizations of it. So how do I make towers from that? Well, if I have a finite index subgroup, then the fundamental domain for the action, so what is this? The gray sort of triangle, really it's a hyperbolic triangle because the lines are meeting at infinity, is a fundamental domain for the action of SL2Z. Any other triangle in this triangulation is a fundamental domain for the action of SL2Z. If I take a finite index subgroup, the fundamental domain for its action is going to be a union of a few of those, and so that'll give me a cover of the base space. Yeah, in that case, oh yeah, anything that isn't obviously drawn by me and isn't attributed to anyone is poached from Wikipedia. So thank you, Wikipedia, for all the images. Exciting. Okay, and as I did with the circle many times, I can play this reduction mod M game with SL2Z. So what is it going to be? Gamma M is going to be the finite index subgroup of SL2Z, consisting of elements that are congruent to the identity mod N. By taking the quotient by the action of gamma M, I get a puncture surface XM, which if M is large enough is a bona fide surface whose fundamental group is gamma M. And again, by taking a sequence of integers, one dividing the next one, i.e. powers of P, e.g. powers of P, I make a sequence of towers. And if I do this with surfaces, the very same Euler characteristic argument, or just a sort of slight variation of it, gives the same rate of growth. Yes?
Just basic question, is there a relationship between M and the number of punctures?
Yes.
Okay.
Yeah. I mean, and there are formulae, but don't know them by heart. But yes, like in the same way that you can compute V1, you can compute the number of punctures. I mean, in fact, maybe this is a good point, thank you for the question, to say that I'm a number theorist. Like very soon, what I will want to do is give them, or what I do actually when I think about it in the privacy of my own home is I don't think of it in terms of the degree. I think of it in terms of the powers of the prime. M is really the invariant that's growing, not the degree. Okay, so after the example of SL2Z, we can do this very, very, very generally, and this is what I'm going to talk about. So we're now in the second section, arithmetic groups and some conjecture. So the general recipe is you take a semi-simple Lie group G. If you don't know what it is, it's fine, SL2. And then you take its subgroup, a discrete subgroup of elements with entries in Z. So I'm putting this sort of in air quotes. P a prime number, gamma P to the N. Since you have a group with entries in Z, you can always reduce mod P to the M. The elements congruent to the identity will give you a finite index subgroup. And then, well, what you need also is a contractible space with an action of G. So it was the circle, it was the real line in our example of the circle, it's the hyperbolic plane in the next example. And the output is going to be a tower of quotients. So from now on, xn will mean xp to the n. I'm finally committed to taking of a prime. And okay, well, I've started talking about this because of Augustine's question, but the degree grows like p to the dimension of the sort of knowing the, in this construction, the degree of the nth cover only depends on the dimension of the group. So let's rerun the example of SL2R with this machine, with this sort of as a piece of this machinery. In this case, G is SL2R, gamma is SL2Z. If I take SL2Z, I'll get cusps. I can take a quaternion algebra, so variant of SL2Z if I want something compact. P a prime number, gamma P to the N, elements congruent to the identity mod P to the N. The space I act on is the hyperbolic plane, and what I get is a tower of surfaces with where the degree is proportional to P to the 3N. If I'm bold, I can go a little farther and look at let G be SL2C. Inside of it, this is why I was saying with entries in the integers in air quotes, really in that case, I'm going to take SL2Z bracket I. So the Gaussian integers, or a variant if I want compact spaces. Here I can take P to be a prime of C bracket I, about half of the primes of Z or primes of Z bracket I. So if you haven't thought about this in a long time, you can take a prime of Z. You have a 50-50 chance of hitting a prime. And again, gamma P to the N are the matrices congruent to the identity mod my prime, and the space I act on in this case is hyperbolic 3 space. So SL2C has an action on hyperbolic 3 space. And what comes out, a tower of hyperbolic 3 manifolds. Xp to the N, in this case, the degree grows like P to the 6N. So the group SL2C is 6-dimensional. Okay. let me tell you what we know in the case of arithmetic hyperbolic through manifolds. So these congruence towers. That'll give you a sense of sort of, I mean, I told you about circles, told you about surfaces. We don't know everything yet about through manifolds. It's okay. 1976, Milsom creates a tower with unbounded first Betty number. So we know that the first Betty number is not proportional, is not bounded. Now maybe the first Betty number is proportional to the degree. No, it's not. So de George-Wallach in 1978 showed that in any towers where the quotients are compact, actually the first Betty number grows more slowly than the degree. They don't say how much. A year later, there's a result of, okay, I'm sorry if anyone is Polish, Dojek, and sort of combined with the result of Kazhdan shows that in general, the first Betty number grows more slowly than the degree.
In general?
Any tower of hyperbolic manifolds, maybe you need nested normal subgroups that go to the identity.
So what happens?
So still arithmetic, for example, like it's still this congruent setup, but I no longer assume that the thing.
In the previous cases.
They had to do analysis, like if there were cusps, like I guess the proof in the second bullet point is an analytic proof, and if your thing is compact, it's just much easier. There's like no convergence.
No. What happened? Like in the previous case, we saw B1 did grow.
For three manifolds.
Okay.
For three, yeah. Surfaces, it grows like the degree. This is for hyperbolic three manifolds. It is my intimate conviction that Kazhdan had proved this third result in 1971. I spent the entire morning scouring the literature. It's very hard, and I wasn't able to sort of prove it. But I'm pretty sure that Kazhdan's are sort of be at the top of this list. Anyways, the late 70s were sort of a hot era for this topic. So were the late 2000s. I'm sure that things have been proved sort of in between, but talking from my perspective, I guess. Okay, so in 2006, Caligari-Dunfeld create a congruence tower where B1 of Xn is identically 0. So different towers can give you different behaviors, conditional on some minor technical details. So the entire sort of Langlands for GL2 over quadratic imaginary field and DRH. In the same proceedings, Boston and Ellenberg actually show that those two assumptions are unnecessary. And just do it by they take the same group of Caligari-Dunfeld and they study it by sort of P group methods, and they reprove the result unconditionally. There's a bunch of people here who are in the congruent subgroup property seminar. So the group they're studying doesn't have the congruent subgroup property, but what they show is that it has a 3 version of the congruent subgroup property. So any subgroup that has a quotient that's a 3 group is a congruent subgroup. That's what they use. So it's a 3-powered. Okay, here we get our first uniform bound as far as I can tell. So actual power savings. So Caligari, Emerton in 2009, some Iwasawa theory methods show that the first Betty number grows almost as fast as, or is bounded by dn to the 5/6 if the SNs are compact. And finally, we have some towers where really we have sort of a lower bound, the rate of growth. So Kiemke-Schwimmer in 2012 created a congruence tower with B1 of Xn at least dn to the 1/2. This is sort of to give you an idea. Sort of 40 years of sort of piecemeal results is what we know about hyperbolic through manifolds. Hyperbolic arithmetic theorem. Okay, now I'll tell you about higher dimensional manifolds because that's what I think. So the leading conjectures here were made by Sarnak and Schwein, maybe 1990. And so they're very general, and I've sort of specialized them to hyperbolic n manifolds and right below complex hyperbolic n manifolds, just to give you an idea. So let Xn be a tower. Tower will always mean p power tower of congruence. So let Xn be a p power tower of congruence compact hyperbolic n manifolds, then they predict a certain power saving. And so, okay, there's a little epsilon. So for every epsilon, there's a constant such that, well, and the constant depends on epsilon. That's why there's an epsilon in subscript, and what's sort of worth, I mean, this is a formula, formulas are annoying to look at, but the point is that the bigger the space is, the higher dimensional the space is, as n, capital N grows, the smaller the proportion, the fewer first homology classes there are relative to the degree. So the slower the growth of B1 is relative to the degree. Very similar conjecture in the case of complex hyperbolic manifolds. And via tower. Congruence, compact, complex hyperbolic manifolds, so real dimension 2n, i.e. the group that you start with when you run the arithmetic groups machine is un1, then in that case should be 1 over m plus epsilon. Okay, for the experts in the room who have patiently listened to all my stories about the Euler characteristic, reasoning for the conjecture here is that the classes in H1 should violate the Ramanujan conjecture. And we know the Ramanujan conjecture is false, but it shouldn't be too false. And so whatever classes violate the Ramanujan conjecture, there shouldn't be many.
Could you recall Ramanujan conjecture?
I'll tell you sort of in private because it's gonna says something about square integrability of matrix coefficients. I've sworn that I would give this entire talk without saying the word representation. So that's why I won't. Okay, what? Okay, so let me give you an approach, sort of an idea for a strategy based on these CERN-Actuate conjectures. So what does the conjecture say? That the rate of growth should be very slow relative to the degree, particularly if this if the manifold has high dimension. Okay, well, I've told you that in congruence towers, the degree grows like p to the n times the dimension of the group. Here's an idea, which is not mine. I think it's Peter's. Is it the case that the growth is slow because it actually tracks it actually is proportional to p to the n times g prime for a smaller group g prime. So sort of because the growth of B1 tracks some information that's actually known by a smaller group. And so do classes in H1 come from a different tower associated by a smaller group? There'll be a lot of air quotes in the next few.
H1 here is the homology?
Yeah, H1 is the homology.
Can you say again real quick what you mean by the second bullet point?
Can I what? Sorry. Yeah.
What you meant by the second bullet point?
I mean the answer.
What is the hypothesis?
So we predict that these classes, I'm about to sort of spend the next 20 minutes, but not we. So I actually predict that the growth of B1 should be slow. And an idea is that it should be slow because all the classes in H1 that you're counting as you go up the tower, they're actually in bijection via sort of Langlands functoriality, which is what I'm going to talk about for the rest of the talk, with some classes on a tower of covering spaces associated to a smaller group and which is sort of forced to grow slowly. Should I try to repeat a third way?
No, I don't understand what you mean by a tower coming from a group G. I mean, a tower is defined by a sequence of congruent subgroups.
Yeah, it is.
Right.
But I can play the congruent subgroup game with, for example, U21, or I can play with U31. Is it the case that the classes in B1 that come from U? I mean, this is what I'm going to talk about U21 and U11 along for the rest of it. But fair enough. This is why there's air quotes. Quotation marks. Okay, so here is the first example of what it could mean to come from a smaller group. So going back to the story of the hyperbolic plane, here I've drawn the geodesic in pink that relates the golden ratio to its conjugate, so 2 points on the real line. And that geodesic is preserved by a copy of GL1 Z minus root 5 inside of SL2Z. I've even sort of shown you what it is, some subgroup inside of SL2Z. And so here is a smaller group, GL1 Z minus root 5. And it gives rise to a loop in the quotient. And so would it be possible to sort of count these loops coming from different groups, and by showing they're non-homologous, I don't know, getting some sort of control over them, get bounds on the growth of cohomology. So that's actually the first theorem I told you about hyperbolic three manifolds. That's how Milson produced his towers with unbounded first Betti number, was by showing that he had, that as you went up the tower, there were sort of more and more of those cycles coming from smaller. That is not what I'm going to talk about. What we use, and I'll tell you in a second why I said we, is a spectral approach. And I gave this talk as a practice to an algebraic topologist, a friend who's an algebraic topologist, and she was like, "What spectrum?" I'm like, "What?" So what I mean here is that there'll be a family of operators, and I'll sort of study their spectrum. Okay, here's a theorem. So I'll read the theorem and then I'll make some comments about it. So if P is a prime that's large enough, and gamma P to the n is a sequence of co-compact congruent subgroups of UN1 have associated symmetric spaces, and are under assumptions on P, so this theorem was first proved by Marshall and Shin in 2019, or on N, so they throw out half of the primes, I throw out half of the N's. We give an upper bound for the growth of the first Betti number. What I should say, I should give full credit. So the theorem that Marshall and Shin prove is much, much, much stronger than this. They give upper bounds for the growth of all Betti numbers in this case. And in fact, sort of they go around the co-compact assumption by studying L2 cohomology. The theorem is much stronger than this. And while I'm sort of giving credit where it's due, my theorem is also much stronger than this. So the hypothesis that I relax is that I can work with any unitary group UAB, sort of any signature instead of UN1. So this sort of hyperbolicity assumption is removed. So this statement is really the intersection of our two theorems, but it's the one that's suited to this talk. Okay. So again, let me remind you, these are complex hyperbolic n manifolds, so they're real dimension 2n. Do we beat Sarnak-Chouet? Well, we not only confirmed the predictions of the Sarnak-Chouet conjecture, but we beat it. In the conjecture was a 1 over n. We managed to sort of sneak a little n plus 1 over n plus 2 on top of that. So in fact, the prediction, the growth is even slower than the prediction of Sarnak-Chouet. And finally, in both proofs, the ideas are similar. So we use Langlands functoriality to show that the cohomology classes on our group UN1 mirror some classes on a smaller group. And we count classes. And for the entire, for the rest of the talk, I'll sort of keep this example, like we'll drop this capital N. In the case where G equals U21, the xn are fourfolds, so they're complex surfaces, real fourfolds. In fact, sort of the grandfather of both of these theorems is the theorem of Simon Marshall from 2014, in which he showed that d1 of xn grows like dn to the 3/8. So I've just sort of plugged in the correct numbers for n equals 4 here, i.e. p to the 3n. What I should say is Simon in that paper actually he shows its chart. He makes a tower where the cohomology grows that fast. So yeah, he shows his chart in the sense, yeah, exactly. He finds one example in which the cohomology, or he finds examples in which the cohomology grows. Okay, how do we do it? So here comes the spectral. First, instead of working with homology, we're going to work with drawn cohomology. So the spaces are in duality, so they have the same dimension. And really, sort of by theorem of Hodge, classes in H1 are represented by harmonic one forms. So instead of counting loops, what I'm counting are harmonic one forms. And so the new problem, here is where I say I'm trying to solve a PDE. What is it called, the heat equation? So the new problem is to compute the dimension of the space on harmonic one forms on Xn as n goes to infinity. So it's much more like a Weil law problem really than a topological problem, except instead of changing the eigenvalue, I go up the tower. Okay, and so the strategy is to show that these harmonic one forms match up with Laplace eigenforms with maybe a different eigenvalue on spaces Xn Yn associated to a different. And you could tell me, Mathilde, there's a lot of Laplace eigenforms in the world. Which ones are you going to choose? And so the problem, find Laplace eigenforms on some other space is under constraint. And so our solution is going to be to add more operators. So instead of just thinking about the spectrum of the Laplacian, we'll think about the spectrum of other operators. So these are the Hecke operators. So I'm a number theorist. The reals are but one completion of the rational numbers. There's a different completion for each prime p. And so for me, the Laplacian, which comes from the smooth structure, I guess, sort of the real thing, has a p analog. So I keep saying prime number p, but here it's prime number L because we've already reserved p for the tower, the level of the tower. For each prime number L, there's a Hecke operator which plays the role of an L analog of the Laplace. All these operators commute. So the Hecke operators are on H1. And so what that gives us is a basis of H1, which is a simultaneous eigensystem for all these operators, delta. And so what we get is from classes in H1, we get eigensystems. So here psi infinity is 0, since I was looking for harmonic forms, and psi 2, psi 3, psi 5 will offer all primes. And what we want to do is to now find these eigensystems in spaces built from other groups. Okay, so the Langlands functoriality conjecture predicts, gives us sort of a cue for where we should look for these. So predicts other groups H for which such a system of eigenfunctions will appear. I would love to tell you that it's in subgroups of G. Sadly, this is not the case. So it's in groups H such that the dual of H is the dual of the subgroup of G. See that I have a bit of time, so let me tell you. When during COVID, I watched a lot of TV. I watched Buffy the Vampire Slayer and also Star Trek Deep Space Nine. And in both those shows, there's various episodes in which there's like a mirror universe in which all the good guys are bad and the bad guys are good. And so this is a little bit how I think about the dual side. You have sort of your groups, but there's a dark side on the other side in which sort of whatever happens, it's not exactly the same thing, but there's a correspondence between the two sides. I'm so glad that Langlands is no longer here.
What if he's watching on the Zoom?
I can tell you he isn't. Anyways.
It's not like it's recorded.
Yeah, exactly.
For any price, we can remove anything you want.
Okay, so eigenspaces, eigensystems, or these Hecke eigensystems that I was talking about that are indexed by the prime numbers, including the prime at infinity, correspond to conjugacy classes in the dual group. And if the conjugacy classes actually belong, all of the conjugacy classes for all primes belong to a certain subgroup X, then what Langlands functoriality predicts is that there should be associated eigensystems on spaces that you build from H. I think I said X, I meant what is written on this slide. Okay. So the good thing about these conjectures is some of them have now been proved. And so the endoscopic classification of representation proves, so let me read the thing and then tell you about the asterisks. So proves the Langlands functoriality conjecture in the special case of what we call endoscopic groups, sort of endoscopy. It's an instance of Langlands functoriality. I'm not going to tell you what it is, but I'll tell you in the case of U21, which is sort of what we're tracking, or what we're keeping in mind. What it tells us is that our eigensystems show up on spaces that you build from U11 times U1. Okay, prove is because there's a lot of sort of people who've promised they would publish the missing details, and not done yet, but the experts seem to think that it's coming. So I treat, for example, this endoscopic classification of representations. So that's, should say, is pioneering work of Arthur, and then was extended to unitary groups. So at first proved for orthogonal and symplectic groups by Arthur, and was extended for split unitary groups by Mach, and then to all unitary groups by Carreto-Menges.
Arthur proved the case for symplectic groups.
And orthogonal, yeah.
Okay.
Yeah. But quasi-split. Only quasi-split. Okay, so how do we use the endoscopic classification? Okay, I'm going to stop. How do I use the endoscopic classification? So you go from eigensystems showing up two concrete upper bounds. So you have to sort of make numerical the results of the endoscopic classification. And the first question you can ask yourself is, what are these spaces Yn on which I told you that eigensystems should show up? So here's a picture. Yn is, in this case, just a disconnected zero-dimensional manifold, which the experts call a bunch of points of cardinality Pn. So I've sort of drawn a picture. So this is sort of my last slide that has math on it. And it's a picture of the proof. So I'll try to explain a little bit how things work. So from U11 cross U1, you sort of taking a suitable action on a space and a suitable quotient, you create this tower of points, which you know grows like p to the n. This is just a class group, again, for the experts. So using, I wanted to plug the fundamental lemma because it's like, again, a big result in the Langlands programs, worth of Field's medal. It's hard to, when someone asks you what's the fundamental lemma, you're like, the fundamental lemma in this case tells you what tower to go up. It tells you that if you're going to go up the p power tower in U21, you should also go up the p power tower in U11 cross U1 to sort of constrain the primes along which you can go up the tower. And then a variant of the fundamental lemma for congruent subgroups that was proved by Ferrari just a little bit after the proof of the fundamental lemma tells you, sort of gives you the, tells you that these classes are not exactly in bijection. There's sort of at each level, the classes in the bunch of points sort of give rise to p to the 2n classes in homology. I've drawn these fourfolds as surfaces because I can't draw four-dimensional manifolds on the left, the four-dimensional. So the picture is, you can count the classes on the right, and you know how many classes on the left they give rise to. And what you don't know is whether there's cancellation, which is why this is just an upper bound. But Simon was able to show that in some cases there isn't much cancellation. And in that case, we noted that the counts are sharp. Yeah, and so this is sort of a sketch of the proof in picture form. Yeah, and I think that's about all I wanted to say. So thank you very much.
Thank you very much.
You often draw the bottom of the tower. So you're like, oh, H1 grows, but H1 is never really big. But I think like this picture has a very large first Betty number. What is this picture? It's a piece of art.
Do we have questions?
Yeah.
Some point you said that the growth depends on the sequence and not on the fundamental group. And to what extent somehow I vaguely remember that there are some conjectures.
No, definitely. Sorry.
Yeah, no, that if you take a sequence which is really separating, like, you know, going all the way to the identity, then somehow the rate of growth is the same or things like that. I mean, I remember vaguely, but
so here is what's true. The degree, which is just sort of the index of the subgroup. If you're working with congruent subgroups, you can compute it. I mean, it grows like p to the n to whatever the dimension of the group. I mean, on the other hand, the Betty number
as a function of the
that can go any. I mean, as I was saying in the examples for three manifolds, for example, there's this tower of aspherical manifolds, so sort of for which the Betty number is 0 all the way up the tower. But on the other hand, Kionke-Schwimmer have also created these towers in which the first Betty number grows like faster than the degree to the 1/2. So no. So I am not saying that the rate of growth depends only on the prime. And in fact,
but somehow if you take, I mean, I vaguely remember, but there was question. If you take a tower, which is really, you know, kind of going deep enough, okay, you can say, let's assume that for every subgroup finite index, there is some finite index.
So that's true. Right. So I'm not a three manifold theorist. at all.
No, but even in a general,
But no, but for example, like every, right, this, I'm gonna say, but this like virtual Hagen conjecture says that every subgroup has a finite cover, or sorry, every three manifold with probably like correct adjectives has a finite cover with non-trivial first Betty number. And so here I'm talking about a very, very, very specific tower. So I'm taking about towers of full level co-compact p-powers subgroups. And actually, even in the,
I think what you're doing is true for any congruence family. I think Lapid and maybe Finis prove quite I mean, if you're in a higher rank, then these things always Binyamini Shram converge to the universal cover.
mm-hmm.
And if you are congruence, then that's still true. Like even for SL2 subgroups of SL2Z, there's a theorem of maybe Thompson that the genus of a congruent subgroup grows like the index divided by 12 or something, I can't remember. So if you put the congruence condition quite freely, I mean, you're looking at 1' and powers, but that's typical.
Yeah. So maybe I should have said that. I mean, even in Marshall Shin, they don't go up a p-power tower. They go up a sort of tower of any.
Right. So the congruence behaves kind of Binyamini Shram convergence.
you don't remember what's the result. This is exactly Luke theorem, right? If you take,
Yeah, exactly.
if you normalize,
Yeah, but Luke's theorem tells you that you converge to the L2 Betty number.
right?
But in this case, the L2 Betty number is 0. So what we ask is,
So
How it's working.
refine.
yeah, exactly.
But if I can tell a story about the fundamental lemma,
Go for it.
only if the questions are finished. Okay, I'll tell a quick story. So when the fundamental lemma was proved, a fellow from Newsweek was asking around, what are the big breakthroughs in math they want to write about? So somehow they landed calling me up, and I started telling him about this theorem, that theorem. And then I said, there's also the fundamental lemma. He says, what's a lemma? I said, well, that's kind of a small theorem. And you say this fundamental lemma is a big result. And he got very caught up in the language. And then he decided this was something he had to write about. And it made it as the top Newsweek's top science achievements of that year, the proof of the fundamental lemma. So you have every right not to describe it.
I'd like to thank the speaker again for a really beautiful lecture. Thank you.